It's probably true for high school teachers too. I mean, you want that job. It's not that you can't get another job, but you want that particular job. What are you going to do with your master's?
I'm going to keep teaching high school and enjoy it. Hopefully I'll get a better schedule out of it, but also it depends on how things are going, because once I have a master's, not only can I teach what we consider college level, like the AP calculus, but also I'm certified in physics, so I can also then teach that. Because we have one teacher who may be retiring, and I'm not sure if it would be easy or not, because honestly, the problem with teaching Algebra 2 or Algebra 1 or anything like that this year is that part test is the same.
Right, I know about that because of the board, and also here we're involved in it.
Yeah, and honestly, like the level they put it on, like it's wonderful and rigorous, but I teach at a technical school, and I can't necessarily say for sure that while the ideas are beautiful, and if kids go into college, it's a wonderful level of rigor. You enjoy the kids coming in if they could meet that in high school. But I have kids who are welders and plumbers, and I'm not sure they need really that level of abstraction to say that they graduated from high school. So I'm not sure if it's going to be too much.
Well, if it's going to be too much for your kids, it's probably going to be too much for a lot of kids around the state. Remember Taylor Series? I put it in summation form. I like what one biology student once said. They were watching me do Taylor Series, and he said, you know what a Taylor Series is? It's a model of a function. That's what it is. You're modeling functions using polynomials. And there's many ways to model functions using polynomials. There's many formulas out there. There's something called Lagrange interpolation where you can just do data fitting. But the unique properties of a Taylor series is that you have to have the derivatives and the slopes all match up. So you can do this nice explanation of a Taylor series by actually drawing the first term is just a constant right at the point that you're interested in. So you can draw this nice, beautiful picture. Here's my curve. Here's my x0 where I'm going to center my Taylor series around. If f at x0 is the best constant approximation of that point, then the tangent line becomes the best first order approximation around that location. And so each one progressively gets supposedly better and better under certain conditions, which we don't talk about in Calc 2 too much. But here we talk about this. It's not enough to have it be C infinity. Well, you obviously need it to be C infinity, otherwise you can't take the derivatives and plug it into this formula. Calc 2 actually, not Calc 3, but we know from Calc 2 that the formula may not even converge. And in fact, usually this is taught at the end of the semester. The way it's taught is you learn all the different convergence theorems for series, and then you get into the finale, which is Taylor series. And the whole idea is that you learned all these convergence theorems to apply them to Taylor series to determine when the Taylor series converges or doesn't converge. And that's because you're trying to model a function by a polynomial, and you want to know when there's agreement between the function and the polynomial and when there's not. The set of functions that are C infinity, because you at least need that, you need all derivatives to exist, where the Taylor series converges at least near that x equals x0, those set of functions are called analytic functions. So I just wanted to remind you how to calculate one of these, and I actually gave you some homework with it because we're going to do a lot with series. This is just the tip of the iceberg for series. Series solutions are actually very cool. The whole concept is very cool. So just to remind you, what you do to calculate a Taylor series is you find all the derivatives of the function. And so I just took the derivatives for you. Then I left it out here, but you get a minus coming out in front, but you also get a minus from the chain rule. So the two minuses always cancel out, but I put it here in the other ones. And every time you're taking this power up to the front, you're going to get 3 times 2. Now you're going to get 3 times 2 times 1. Like every time you're going to get another one, so you're going to get a factorial. Then in every one of these derivatives, you're going to plug in the point that you're centering around. You have to have some viewpoint where you're going to model your Taylor series at. So I just chose 0 here because it was easy. And we plug it in, and we actually get the constant. And this gives us the coefficient of the power series. Then you plug it straight into the formula. That's the formula expanded. And you get what's known as the infinite geometric series. So I love graphing these, and I love having students graph it and see it. And we do it at the beginning of the semester, not the end, because I feel like that's the most important thing they're going to learn in that class, not the least important, so I moved it up in front. So we actually get to spend some time looking at these pictures, and I make them actually find the interval of convergence graphically, and then find the interval of convergence analytically, so that they can see why they're doing what they're doing, because it's a pretty neat application of what they're learning. So here is the one with the asymptote here is the 1 over 1 minus x, and this is the polynomial. And what you can see from this image is there's good agreement of the polynomial and the function in between -1 and 1. And you probably can even see that -1 is included, but 1 may not be included. And in fact, that's what you find when you do the analytic side. You'll find that the interval of convergence by the ratio test is -1 to 1, and you get this -1 using the alternating series test. And over here you get no agreement. So ratio test gives you the everything but the endpoints. So what we do know analytically is that Taylor series converges in this region, -1 to 1. And it converges exactly to that function. So we say f of x is analytic at x equals 0, because there is a region around it where it does converge. I always think I learned this in PDEs or ODEs. Somewhere I memorized all my important functions. In fact, old school differential equations would always look at series solutions, and I had a professor in undergrad who would just look at these crazy series and go, oh, that's cosine 2x divided by tangent. You know, he would just see the whole series. Like, he was so used to working with the series, and that's how they did things. We don't do that. We don't have that skill anymore because we have computers that will simulate our solutions for us. So there's no, I mean, in some ways it's obsolete. But to do our theorems and proofs, we still have to use series. And sometimes when you have nothing left, that's the best approximation. Just assume you have a series solution, stick it in there, and try to yank out the first 3 terms or so. Are you guys using that in your research, taking series and you've done it? Yeah, I'm sure that's a usual technique. Have you done it?
No, mostly numerics.
Yeah, it's just too easy. I mean, honestly, if I had a differential equation, I would go to Maple and say desolve before I go do this.
Mostly tied to ODE stuff.
Yeah, but we can do, and in fact, it's less useful in PDEs because it's a little bit harder to get at. But when all else fails, you can do this. So I gave you some homework on this section on Taylor series, not to get you to learn Taylor series because it's just a formula. It's just to get you used to the idea of working with series again, because that's one thing we're going to hit a lot. This is page 99. So I'm going to show you one of them just to show you how to do. It's on page 99. So this is 1 over 1 minus x squared, and they want you to find the Taylor series and identify the region that it converges in. And honestly, you can plug the function and the Taylor series on a calculator or a computer and just see the eyeball test. But I'm going to show you analytically how to do it too. We already have the series for 1 over 1 minus x. I just did that about x equals 0. So one trick you can do, I mean, you could actually take the derivatives of these guys and use the brute force to actually get this Taylor series out. In fact, it's actually pretty cruel because the first derivative gives you a minus 2x out of the inner, the derivative of the inner function, and then you have to take derivatives of quotients as you go along. So I love to show my Calc 2 students, I guess this is on video, how to do this, and then I also show them how to use the formula. And more than anything, they'll just learn the formula because they're minimalists, and I'll give them something like this, and they'll be trying to take the derivatives and look for patterns. Yeah. But all you have to do, though, is take that original Taylor series and plug in x squared for x, and you get the second Taylor series. So it's that simple. And in fact, in the book they ask you, they give you the e to the x cosine x and sine x, and they ask you, can you use one of these other functions to get this? And the answer is yes. You just manipulate them. So how do you find the interval of convergence? The ratio test. I think in real analysis you prove the ratio test, right? That sounds like something you should have done. If not, then maybe we should do it. The hand-waving proof is that if the ratio of an plus 1, that's your n plus first term, is divided by the nth term is less than 1, it's that not just that the terms themselves are decreasing. They should decrease, right? Otherwise you have no hope. If they're increasing over time or if they're constant over time, that thing's not going to converge. But if they're decreasing over time and they're decreasing fast enough at this rate, then the series should converge. And that's the hand-waving concept for it. So step by step, you take the nth term. The students actually had find the nth term because sometimes they couldn't get the nth term, so that was the kind of a process. But then you take n plus 1, an plus 1. So now we have an and an plus 1. Then you formulate the ratio, but we do it in absolute value because we're using the absolute convergence. And then you set that result less than 1. And in this case, when we set the result less than 1, we just get absolute value of x is less than 1. And what the ratio test tells you is, as long as x is inside that interval, you get convergence. When x is outside that interval, you don't get convergence. If x is at the endpoints, you're going to have to figure that out yourself. So the ratio test gives you pretty much everything. Sometimes at this step right here, there'll still be n's left over after you do the algebra. It just happened that the n's disappeared here. If you have n still left over, then you have to take the limit first and set that limit less than 1. So the interval is -1 to 1 that we're given at least. And we don't know about -1, but I bet you -1 still works. So there's specific tests. You learned the integral test. You learned the alternating series test. There's a whole bunch more. The root test and the ratio test are very similar, so that's not going to probably give you any more information. Usually it's either if it's a negative endpoint, it's the alternating series test because you have a decreasing function. That one's pretty easy to apply. Comparison test. Those are the easiest ones to use, the comparison. What does Taylor series have to do with differential equations? Well, they were trying to tell you this in the book, that if you have an ordinary differential equation, you can solve it using the Taylor series, but they just give you the theoretical side of it. So I'd actually like to show you an example so that you can see how to do it, and then when you see how to do it, it makes clear sense. So if I know f is analytic, then f can be expanded into a Taylor series because that's the definition of being analytic. And what the Cauchy-Kovalevsky theorem says, which I'm going to write out in detail later, is that it says that u of t is also analytic and can also be expanded as a series. So if I have a differential equation, here's the easiest one I can think of. Well, actually, the easiest one I can think of is y dot equals 0. But the next easiest one I can think of, y dot equals y. Well, that's analytic. The right-hand side is beautiful. It's got all derivatives, everything converges. Its Taylor series is itself. So we can assume that y of t does have an expansion. I just don't know what those coefficients are going to be. So if I expand that out and write it in long form, I get a0 plus a1t plus a2t squared. And I can take the derivative of that series term by term, which I can do from Dr. Song's linear algebra class because taking the derivative is a linear process. So I take the derivative. And then I pop it up into that equation. So I take the derivative power series, and that's the left side, and the original power series, that's the right side, and I get big ugly mess is equal to big ugly mess. The only way two polynomials can be equal, though, is if their coefficients are equal. So that tells me that a1 has to equal a0 because they're both the constant terms. And I know that the coefficient of the linear term has to equal the coefficient of the linear term. So this guy over here has to equal this guy over here. And I can solve for A2 in terms of A1, and then in turn I can reduce it back to A0. So now I have this much, then I get 3A3 is, and I get A3 is 1 over 3 factorial, and I'm starting to see the pattern. So you keep doing this, and this is what I was telling you, that my professor, Dr. Derrick, would just look at it and go, oh, this is the series for, and he would say not the standard e to the x cosine x, he would say something bizarre, and like, how does he know that? So that's what you find, that if you kept going. Recall that the y of t was expanded in that format, so I can just substitute what I know about all those coefficients in, and I only have A0 now appearing in all of them. So I can factor out that A0 and look at the series that I'm left behind with. It's e to the t, and it's A0 e to the t. Now if I know y at 0 is 1, I can eliminate A0 and I get the functional form, which is y of t equals e to the t. Now, recognizing that series, that doesn't always happen. I obviously took something that I know really well and it's going to work out. But what happens in the case where you can't recognize a series is they'll say, I'm just going to expand this out to order 3. And I have a series form of my solution. That's an approximate of my solution. So that's what you can do. It's a really useful tool, actually.